on to this second tutorial in a two-part series on simultaneous equations. Now, in the first tutorial on simultaneous equations, we just did an example. A farmer was planting barley and potatoes, and we were given sort of a narrative with two different scenarios and data, and we were able to formulate that as two equations and then solve them simultaneously to work out some particular information, particularly for that case, how long it took to sow a field of barley and how long it took to sow a field of potatoes. So that is the main application of this technique in maths, is to take sort of mixed information, solve some equations simultaneously and extract very specific information from it. In this second tutorial, I'm just going to give two more examples. I'm going to give a formal example which is actually related to equations of a straight line, as we'll see, and then I'll do another applied example, which will be someone using various amounts of antibiotic in a microbiology lab. So we'll have a bit of a science twist on the second example. But first, let's imagine that we were given these two equations to solve. So negative 2x take away 3y is equal to 4, and 5x plus 2y is equal to 1. Now, from the tutorials on equations of a straight line, we know that these are actually, in disguise, equations of the form y equals mx plus c and describe a straight line. So these equations are essentially describing two straight lines which are going to intersect at some point. And by solving these equations, we're effectively finding the values of the coordinates x and y where those two lines intersect. But first of all, let's just actually solve them, okay, before we look at the graphical representation of straight lines. Now, what we need to do here really is to try and make two terms the same, either x or y, and we have a choice. We could try and make the x terms the same, or we can try and make the y terms the same. I'm going to choose to do the y terms. So I'm going to multiply equation 1 by 2. And I'm choosing to multiply by 2, you see, because 2 is the number in front of y in the second equation. So if I multiply equation 1 by 2, you'll see in a moment why this is the right thing to do, why it's useful. So I have minus 4x minus 6y equals 2 times 4 is 8. And now you see equation 2, I'm going to multiply by 3. And what will happen then is that this term will turn into 6y. So I'm multiplying this equation by 2 because that's the coefficient of y down here. And I'm multiplying this equation by 3 because that's the coefficient of y up there. And this will give me then the y terms looking the same. So 3 times 5x is 15x, plus 3 times 2 is 6y, equals 3 times 1 is 3. So these are the same equations as these in essence, but here we've multiplied by 2, here we've multiplied by 3, and we've managed to now engineer it so that these terms have the same coefficient. Because one has a different sign, we're going to add these two equations together now. So 15x added to negative 4x will give us 11x. These two terms add to 0 by construction, and then 8 plus 3 is equal to 11. I've chosen the coefficients so that this comes out nicely. So 11x equals 11, and so we can solve this straight away. X is equal to 11 divided by 11, which is equal to 1. And then we can straight away find y. Let's maybe solve it from here. putting x equal to 1 in equation 2, we have 5 times 1 is 5, plus 2y is equal to 1. I can subtract 5 from both sides, so 2y will be 1, take away 5 is negative 4. So y will be negative 4 divided by 2, which is negative 2. And so that's the solution of the problem. Now, let's just see graphically how this all makes sense. I'm going to very quickly turn equations 1 and 2 into equations of the form y equals mx plus c. So equation 1 looks like, I hope I can do this right, I'm going to take the 3y over, divide by 3, I will have negative 2/3 x, take away 4/3, and the second equation will look like y equals negative 5/2 x plus a half. So this is not what you would need to do in solving the simultaneous equation problem. I'm only converting these to our y equals mx plus c form of equations of a straight line just to demonstrate to you graphically what we have actually achieved. So these two equations I can just plot. This is a rather shallow slope that passes through negative 4/3. So it would look sort of something like this. And this is a much steeper negative slope that passes through a half. Would look something like that. And there's the point of intersection. And we have found that point of intersection, you see. So we found that the coordinates of this point are 1, negative 2. So x equals 1 and y equals negative 2. Which kind of is consistent with this very quick little sketch that I've done here. But that graphically is what we have essentially solved by solving these two simultaneous equations. So the bottom line from this first example is that there's a connection between simultaneous equations and equations of a straight line. Namely, if you have two different equations of straight lines and you're interested in where do they intersect, you can solve that problem by expressing them like this and doing simultaneous equation technique to find the values of x and y, which gives you the point of intersection. So let me finish just then with another applied example. So we're in a biology lab and someone is studying two strains of bacteria. So we have strain A of bacteria and we have strain B of bacteria, and it's found that 3 million bacteria of strain A and 5 million bacteria of strain B can be killed with 21 microliters of antibiotic. Okay, so this is kind of a very applied problem that in whatever experimental setup this person has, 21 microliters of antibiotic is enough to kill 3 million bacteria of strain A and 5 million bacteria of strain B, which presumably are all sort of mixed together in some petri dish. In a different experiment, they find that they can kill 4 million bacteria of strain A and 2 million bacteria of strain B with 14 microliters of antibiotic. I'm sorry, my handwriting is getting a bit scrappy here, but it's really these numbers are the key things for us to focus on. So we want to work out how much antibiotic is required to kill 1 million A's or 1 million B's. So let's use the variable A and the variable B, and A is the number of microliters to kill 1 million A's. You see, I had to think there because I've trying to use my units cleverly here. I don't want to have these huge numbers in my simultaneous equations, or I don't want to have this funny unit either, so I'm just going to define A to be how many microliters to kill 1 million A's, and B will be how many microliters to kill 1 million B's. And you see then, by choosing the variables as simply as possible, I can then write the information in these scenarios in simple equations. So 3 million A's is like 3 lots of A. 5 million B's is 5 lots of B, given that A and B represent millions of bacteria. So 3A plus 5B is 21 microliters, and 4A plus 2B is 14 microliters. So now we've taken this, what looks at first like quite a complicated set of information, but we've been able to distill it down by choosing A and B well to get 2 simple equations. And let's solve these. Let's multiply, let's call this equation 1 and equation 2. Let's multiply equation 1 by 4, say. So I'll try and make these terms the same this time. So I'm going to multiply equation 1 by 4, and I'm going to multiply equation 2 by 3, and that will give me 12A in both equations, and I'll be able to solve them. So multiplying equation 1 by 4, I have 12A plus 20B is 4 lots of 21 is 84. And then I'm going to multiply equation 2 by 3. 3 lots of 4 is 12, and that was by construction to get the same term here. And then 3 lots of 2 is 6, and 3 lots of 14 is 42. Now I can subtract one equation from the other. I don't get any contribution from the A's, and then I get 20 take away 6 is 14B, and 84 take away 42 is itself 42. So B then is 42 divided by 14, which is 3. And then I can solve for A, maybe just choose equation 2. You can choose either equation. Choose equation 2, so I have 4 lots of A plus 2 lots of B. We found B is 3, so that's 2 lots of 3 is 6, equals 14, and so 4A is 14 minus 6, which is 8. So A will be 8 divided by 4, which is 2. So those are the solutions. So it takes 3 microliters of antibiotic to kill 1 million B's, and it takes 2 milliliters of antibiotic to kill 1 million A's. And let's just check that that's right. So in equation 1, 3 lots of A is 6, and 5 lots of B is 5 threes are 15. 6 plus 15 is 21, that's correct. 4 lots of A is 8, 2 lots of B, 2 threes are 6, 8 plus 6 is 14. So these are certainly correct. So I hope that's been helpful. Maybe this last scenario was a little bit harder than the typical sort of thing that you might see at this level, given that we had these sort of big numbers like 3 million and 4 million, and you might have ended up with equations with those huge numbers in. But what I've tried to show you is that you can sort of choose your variables so that the equations you end up writing down are quite simple. The most important thing to get from this and the last tutorial is the method of solving simultaneous equations. And this nice modern method of doing it is just to try to find a way of numbers that you can multiply the equations by such that you end up with 2 terms the same. So here we were able to get these two terms the same. Here we were able to get these two terms the same. And what you're typically doing is looking for the two simplest coefficients of the same variable. So here, 3 and 4. You multiply the first equation by the coefficient in the second equation. You multiply the second equation by the coefficient in the first equation, and that way you're guaranteed to then get an exact identical term in both equations, and when you add or subtract them, that will give you 0. Here we subtracted, here we added, we got the 0. We've eliminated that variable, and we're left with a simple equation involving one of the variables that we can solve. When we know the value of one of the variables, we can go back and just plug it into either equation and solve for the other variable. So that's a summary of the method of solving simultaneous equations. Right, I hope that's been helpful, and I think the next topic that we'll be looking at possibly is quadratic functions. I might possibly do some algebra first with you, but again, hope it's helpful, and I'll see you next time.